In this video, I'm going to show you how to prove that the following integral is an invariant. Integral d3p, where this d3p means dp1, dp2, dp3, the three components of momentum. And this is divided by omega, and omega is a function of the momentum because it is defined as the square root of the magnitude of the momentum squared plus mass squared. We want to show that this is an invariant. I have already done that in the course on quantum field theory, but I'm going to do it here as well because there are many details in the course and I would like to concentrate on this problem here. Let's start from the following integral, which we know that it is invariant. In particular, we're going to start from d3p times dp0, so this is like d4p if you want, and if you recall from general relativity, for example, here there was also the square root of minus the determinant of the metric, square root of minus g, but in quantum field theory this is just the Lorentzian metric, therefore this quantity is equal to 1 because the determinant of the metric tensor in special relativity is equal to minus 1. Therefore, we can just consider this to be an invariant quantity, so d4p is an invariant quantity. But we are going to multiply this by a Dirac delta, which will be a function of p mu, where p mu is the force vector related to momentum. So for momentum, which is an invariant. This quantity is an invariant because we are using tensors. And then I'm going to subtract the mass squared of a particle. And this rest mass here, the mass of the particle, is an invariant. We know that from special relativity. Now, what we are going to do is we are going to rewrite this Dirac delta in a different manner, but in order to do that, I have to show you some reasoning that you can do in order to find some interesting formula which is related to the Dirac delta. In particular, we are going to consider some function, and I'm going to sketch it in this manner. This is the x-axis, and this is a function of x. So this is f of x, like this. And we are going to be interested in the points where this function is equal to 0. So there are 3 points here. For example, this one here can be x0, this one can be x1, and you can give a name to that one too. I'm not really interested here. And then I'm going to draw on the right another function. In particular, I'm going to draw the following function, theta of f of x, where theta is the step function. So it will be equal to 1 if f of x is equal to a positive value. So if f of x is positive, this function will give me 1. For example, in this interval here, the function is going to give me 1. Then it will be 0 if the function is negative, so it will be 0 between x0 and x1. We have x1 here, and then it will be 1 because when x is greater than x1 here, it will be positive. So the function is 1 here, and 0 here. Then we're going to do another step, and we're going to sketch another function starting from this graph. In particular, we're going to consider the derivative of this function. So we're going to consider d over dx of theta of f of x. And when we take the derivative of a step function, we're going to get a Dirac delta. So it will be Dirac of f of x times f prime of x. And if we take the derivative here, what we are going to get is, so at this point, which I didn't give a name to, but for example, we can call it x minus 1. So at x minus 1, we are going to get a positive Dirac delta because slightly before this point the function is negative, and then slightly after this point the function is positive. In particular, this function here, so this is the function f of x, but the function theta of f of x will be equal to 0 before the point x sub minus 1, and it will be 1 after x sub minus 1. So we're going to get an infinite value, and this infinite value is the Dirac delta, a positive Dirac delta, whereas at the point x0 we are going to get a negative Dirac delta because the function is decreasing here. So after the point x0 it will be 0, and before the point x0 it will be 1. So we have a negative slope, an infinite negative slope, and this will give a rise to a negative Dirac delta. And then here at x1 we are going to get a positive Dirac delta, and so on and so forth for all the other points. But you should get the idea, and in particular from this graph you can understand that the function delta of f of x times f prime of x, and actually I'm going to consider the absolute value of f prime of x, because if we consider the absolute value, all the negative deltas will become positive deltas. So we have a series of deltas, and you can easily understand that this function will be equal to the sum over n of Dirac deltas of this form, delta of x minus xn, where xn here is simply one of the zeros of the function f of x. Because remember where we started. We started from here. The points x sub minus 1, x0, x1 are all points that make the function f of x equal to 0. So f of x0 is 0, f of x1 is 0, and f of x sub minus 1 is 0. So you get the idea. This is an important formula because we're going to use it for the solution to this integral. Actually, I should not call it solution, but we can easily see that starting from here and using the formula that we just found, we can get that result. So this is what I'm going to do now. Let's rewrite the Dirac delta. So we have, remember that we have delta of p mu minus m squared, and we can rewrite this as delta of p0 squared, and then we have minus magnitude of p squared plus m squared like this, and we are going to define this as omega squared. So we are going to define this just like that. Omega is the square root of that. And now this is our function f of p0. So instead of the variable x, we have p0 here. And this Dirac delta, according to this formula, which we can also rewrite in another fashion. Let me rewrite it like this. We have delta of f of x, and then let's divide by this term. If we divide by that, we get summation over n. And then take a look. When we divide these Dirac deltas by this absolute value, we can rewrite the quantity like this. We have delta of x minus x sub n divided by the absolute value of f prime of x sub n. So we can evaluate this magnitude at the point x sub n because it is multiplied by the Dirac delta, and it is a simple property of the Dirac delta. And we are going to do something similar here. So actually we are going to do exactly the same. But how many roots does this function have? This function has two roots because p0 can be either minus omega or plus omega. So we have two roots, and therefore we can write it as delta of p0 minus omega, which is the first root, divided by the derivative of this function, the absolute value of the derivative, evaluated at omega. So the derivative of that is 2p0, and we have to evaluate it at omega. So we have 2 omega. We should take the absolute value, but omega is a positive quantity because we defined it to be the square root of m squared plus magnitude of p squared. And then we get plus delta of p0 plus omega, and we divide by the same thing, 2p0, but we have to evaluate it at p0 equal to minus omega, so we get minus 2 omega, but we have to take the absolute value, so here we get a plus, just like in here. And that's it. So we are going to integrate this result over p0, because you can see that we can integrate over p0, over p1, over p2, over p3, but we are going to integrate over p0, and we are going to integrate from minus infinity to plus infinity. So when we integrate this Dirac delta, it will give us 1, and also this 1, because if we integrate from minus infinity to plus infinity, that will contain these zeros, omega, minus omega, and so this first 0 here is p0 equal to omega, and this second delta, sorry, is centered at p0 equal to minus omega. They are both positive, and the integration will give us 1. So we're going to get integral over d3p, and then we simply have 1 over 2 omega plus 1 over 2 omega. So we will get d3p divided by omega. And this is the result. So since we started from an invariant quantity, because as I said, this quantity here is invariant, then we have proved that also this integral here will be invariant. And this is very important because in quantum field theory, we have integrals of this kind. Then there are other functions inside the integration, but this element here is invariant. So that's the key point of this video.